Okay, welcome to lecture 28 and possibly the penultimate lecture. So today we're going to look at the KdV equation. In particular, we're going to look at more formal ways of looking for solutions. So last time, if you remember correctly, we looked at basically properties of various parts of these equations. We said that simply this first bit was a nonlinear equation where we saw shocks, and the second bit, if you were to ignore this first bit, you could actually solve it using Fourier method, and you had dispersion. You basically had this idea that you had your initial condition, certain parts of the initial condition was in a certain frequency regime that would propagate with a speed forward, but far enough away in the tail, some of those frequencies would eventually become negative and propagate backwards, and the height of your thing would then just disappear and ultimately be completely gone. In fact, if you look at the method that I called the Fourier method and solve this one, you can use exactly the same method to solve dissipation. In fact, dissipation, you just have ut and two x's over there. You once again just get a dispersion relationship. In fact, it's the question that I asked in the test. So just make sure you know how to have a look at it. But the method is exactly the same, the two methods. And then we said that these two terms, this one tends to form shocks and bunch up the wave. This one tends to disperse it. And what makes this KdV equation so unique is, one, it's exactly solvable, but two, these things actually fight each other and make this idea of a solitary wave that can propagate through that under linear circumstances would not exist. And this is what Russell saw. Okay, and so today we're going to go on and we're going to actually look for these solutions. We also did what we did last time, was look at similarity transforms. We basically said, suppose I were to rescale the solution and rescale all the variables like the time coordinate and the spatial coordinate, and possibly add a constant. What would be the conditions be on those things that I would once again get a solution to my equation? And we worked out all those possibilities, and then we transformed it so we could see what other possible equations were disguised as this KdV equation. Okay, so let's start looking at solutions in a formal way. The first thing is, because of the experiments, the first thing that you do is you tend to do that similarity transformation. Then you tend to make guesses at what the form of the solution would be and work out the consequences of that guesses, because those are easy. And then I'm actually going to sketch to you what the general way of solving the problem is. It's a very beautiful method. I don't expect you to be able to do it, but I do want you to have a feel for what the thinking was behind it. Okay, so the first way is we want to seek traveling wave solutions. And we already know what a traveling wave solution is from the advection equation. We're simply going to say, we assume our solution has a specific functional form where this eta is simply x minus ct, because we know from when we solved the advection equation and we solved the wave equations, this basically, if you write it in this way with this eta x minus ct, you have a wave that's moving to the right with a speed c, and so we're going to basically make this ansatz, push it into this equation and see if there are any solutions. They need not be. Okay, it might not be possible to find a solution that has this form, but then we'll know that as well. So let's do that. So c is a constant, and it's the same way. We simply work out what the derivative of u with respect to t is. It's just f prime times dx c dt, so it's just minus c. Ux is just f prime because x just enters linearly in there. U triple x is just f triple prime. And so then we take this and we substitute it in there, and we call this the restricted KdV equation, and it's this equation. Okay, so this is no longer a partial differential equation. We have decreased the order of the number of independent variables by the ansatz, and so the statement is, if we can solve this problem, we can get a solution of this form. So then we have a solution to the KdV equation. Okay, so the first thing to observe is we can integrate once, right? That's easy. This is just f squared's derivative times a half. This is also just a differential. So we can integrate once, and so we get minus CF minus 3f squared plus f double prime is equals to a. Okay. Where a is a constant, and then it's a normal technique you would have learned in the second year. You put p equals to f's derivative. Okay, and this technique you generally use if your independent variable does not appear in the right hand side. Okay, and you have a second order derivative. So you put p equals to f prime, and you work out dp df, which is simply dp dxc dxc df, and that's equals to 1 over df dxc. Okay, and the reason I did it this way is that this is once again just p. So you know that dp df is simply equals to 1 over p times dp dxc, and dp dxc is just double prime f, so it's equals to that. You then go and you replace f double prime by basically a plus cf plus 3 f squared, and what you get is this thing. Okay, so f double prime is here on the left hand side, and I've taken this p and I've multiplied it through there. So you have now got a first order differential equation for f, where you can consider the independent variable to be f. Solving for p, you basically can write this as a half dp squared, and then integrate this guy with respect to f. Okay, so if we integrate, that's just a half dp squared on the side, and then you just have to work out the integral of this thing with respect to f. So it's simply af plus c over 2 f squared plus that the integral of that thing is simply f to the 3 plus your integration constant b. Okay, so we've now integrated our third derivative, and we're only left with one derivative with respect to p. And before I go further, it's actually easy you can generally integrate this thing because it's basically the square root of a cubic, which you can always do if you can always find that. In fact, you can always find the square root of a quartic. But they are nasty functions, and it becomes much easier if before you go on, you impose the boundary conditions. And we're only going to be interested on functions that are bounded at infinity. So we're going to assume basically that f and f prime and f double prime goes to 0 as c goes to plus minus infinity. And so f prime is basically p. So if c goes to 0 to infinity, you have this going to 0, you have f going to 0, and so we know that b goes to 0. Okay. We also know from up here f double prime is just dp df. We know that that goes to 0, so this side goes to 0, and f goes to 0, so we know a goes to 0 as well. So we set these two constants, and then we get a much easier thing to integrate. Okay, so we're left with this guy, and so we now want to integrate it. You're either going to have a fantastic memory from your second year, or you're going to look it up in integral tables, or you're going to ask Google, and all of those things are fine. Just make sure that the answer Google gives you makes sense if you're differentiating it. Okay, so I know, so it's f prime squared, so it's 1 over the square root, because you have to put all the f's on the right hand side, of df over 2 times 2f plus c. Okay, and whenever you have a square root like this, you usually either have a trigonometric substitution or a hyperbolic trigonometric substitution, depending on your integration bounds, which we don't know. And so generally what I'm going to do is I'm going to say let f be one of these functions, so that the stuff under the bracket, if I get a complete square over there. The reason I opted for hyperbolic functions is the assumption that f is bounded between like 0 and 1 isn't there. If I knew it, if there was a fixed boundary where it was like going between two fixed numbers, then I would have chosen tan or the trigonometric ones. Because I potentially want to consider f's with infinite height, I'm guessing it's going to be this, right? And then all I wanted is something so that if I work out 2f plus c, then I have a complete square. And then whatever I get in the denominator, I want as much as possible of it to cancel when I take the differential of f. Okay, so those were the guiding things, and then I either get my textbook or I look it up. So in this particular case, the other reason for guessing this is because I know what the traveling waves look like from Russell's experiments. So I want a hump that's traveling, and this will make it for me. Okay, so there was a physical reason for guessing this as well. Okay, so we say let f be this. Okay, and there we get immediately that I can get rid of the square root, because the sec squared identity is simply 1 minus tan squared. Okay, so the moment f is equals to that, 2f is equals to minus c times 1 plus c will disappear, minus minus, so then you'll have basically square root c times tangent of h, and then you've cancelled out your square root. Okay, this f is still messy, it's still your square, but you have this df that then becomes a saving grace, because df of this thing is once again sec squared times tangent. So you have this spectacular cancellation that basically says that this integral then is equals to the integral of d theta square root c, which is equals to plus minus the integral of dxc. Very convenient. So you now have that theta is equals to minus plus the square root of minus plus the square root of c over 2. And these factors you must be careful with. You mustn't just throw them away, because they actually are going to relate the speed of the wave that's traveling to the actual shape. So here you get that theta is equals to this times xc minus x0, which is just a constant. And recall that xc is effectively x minus ct. Okay, and then you have, if you put this back into the solution, you have the general form of your solution, and what that general form of the solution is basically this thing. Okay, the only reason why I said you should say f is even function of theta, it was basically because you have to be careful. Here was two potential solutions, but they're actually the same one. Okay, so that's the reason I made that comment. Otherwise, you would basically have written out the two possibilities. So you now have f of xc, which basically f minus ct is simply equals to minus c over 2 sec squared, the square root of c over 2 times x minus x0 minus ct. Okay, so there are a couple of things to observe here. Remember when we did traveling waves for that vection equation, f, there was no restriction on f, right? It could be any shape and it would just travel. If we make the traveling wave ansatz for the KdV equation, we've just derived that it has a very distinct shape. It can only be this bump. There's no other solution that is a traveling wave solution, okay? But it does exist, which was there are a lot of other equations that I've tried doing the same thing with, and it just doesn't give you an answer. Okay, so it does exist. And if it exists, it has this very unique property that was actually experimentally observed. I really don't mind if you, because I'm very far from you. There was this thing was experimentally observed that the speed of the wave had a certain scaling with c, okay, and that the amplitude had also a scaling with c, and this we see over here. Okay, so the higher the amplitude of the wave, the faster the wave will move. Okay, and that you can see. There's a direct relationship between what the wave looks like and how rapidly it transports itself. Okay, so let's see what it does. So suppose c is equals to 0.5. What I'm going to do is basically plot the solution at the initial time t0, and then I'm going to plot it at a later time t12, say units later. So if c is equals to 0.5, this is what it looks like. If c is equals to 1, this is what the solution looks like, so it's moving faster. If c is equals to 1.5, this is what the shape 1.5, this is what the shape looks like. And so you can go on. The faster, the larger c is, the bigger the wave, the more rapidly it moves. Okay, so that was 0.25 and 0.3. And so you can actually see the progression. So this just gives you a feeling of what a solitary traveling wave solution actually does. What is also interesting, in fact, is the wave remains a fixed shape, which is there's no reason why it should be that way, but it does, and it's due to the competition between the nonlinear term and the dispersion. And the height and the shape depend on the speed. Okay, so I'm just writing down only. And what is also interesting is if f is less than or f is always less than or equals to 0 for traveling waves, because of this minus sign that came in with the derivation, and that is a rigorous. It's not a mistake. And in fact, what can also happen is there's a lot of things in partial differential equations that people can find a solution. Like you can find a solution where the shock wave does a thing like that, but it's not a stable solution. If you knock it a bit, the wave's going to break. And so what you usually do when you find solutions is, one, you have to find the solution, and then two, you have to prove that it actually is a stable solution. So in relativity, that actually took 20 years or more. Schwarzschild, it was easy. So what you do is you find the Schwarzschild solution, and then you say, okay, fine, let's look at the Schwarzschild solution plus perturbations around it, and then you work out whether all those things are stable or all of them decay to 0 or not. Okay, so that one is reasonably easy to show. The Kerr solution, people took a long time to actually prove that it was stable. It is, but they couldn't show that. So often to prove stability is quite a hard problem, because you actually have to look at whether the solution attracts, and there are techniques for doing it, but they are intensive calculation. Anyway, so this solution here has basically been shown to be stable. Okay, and to compare this with what we actually saw in Russell's, this KdV equation is related to the equation that actually describes Russell's or the shallow water waves if you simply replace u with minus u. Okay, so the waves, remember Russell's waves were waves, not waves of depression, but sort of humps. And so the relationship is just u to minus u. Okay, and then it's exactly the shape that Russell was actually observing, and you can check. And people have done it. Okay, so this is the first sort of formal derivation of traveling wave solutions. This set of equations has different solutions as well. Okay, and what I'm going to do next is I'm going to, like the heat equation, I'm going to look for the self-similar solutions. What is interesting about the self-similar solutions is we haven't really seen them that much because they explode after a finite amount of time. Okay, but they do exist. So I'm just giving you a feeling of, once again, differential equation, systematic ways of attacking it. And then I'm going to actually give you a flavor of what the general means of solving it is. It's a bit involved, but the idea behind it is very, very beautiful. Okay, so self-similar solutions, we showed that the equation was invariant under similarity transformations, and by similarity transformations, remember it was the discussion I had in the previous lectures. Basically, if you have a new variable x, which is just the old one rescaled, a new variable t, which is just the time rescaled in a related way, and u equals to u over gamma squared, then you can show that you basically have this identity that if u is a solution, then this thing is also a solution. Okay, and we're now going to use that, and I said whenever you have this, you can find similarity solutions. And so let's just find them, or simplify it till we can say something about them. Okay, so once again, we want solutions that have this for all gamma, x, and t, and then the simplifying assumption is basically, let's set gamma equals to t equals to a minus a third, and basically the aim over here is to remove one of these independent variables, and once again reduce your system to only having one independent variable. Okay, so you typically set this guy to 1, and then whatever remains as a result over here you set to the new variable. So that's x over t to the third. Okay, because gamma is simply 1 over t to the third. Okay, and so now we're looking for solutions where x has this particular form, or you can equivalently write it like that. Okay, so very, very similar to the method that we used to seek the traveling waves, except that the ansatz we are now making for the form of the solution is slightly different. Okay, and so once again, you can work out the time derivative. It's simply the product rule, the time derivative of this first one multiplied by g plus t to the minus 2 over 3 times the time derivative of g of eta. So that's g prime times the time derivative of eta, which is simply ddt of this thing. So that will be it will be a minus a third times t to the minus 4 over 3. But then I take out another one so that I can place the x with eta again, and I am left with whatever remains times minus 2 over 3, which will give you this term. Okay. And you have u of x is just ddx of g of eta times basically, so it's basically t to the minus 2 over 3 times ddx of g of eta. So that's g prime times d eta dx. So it's just times a third. So, sorry, 1 over 3. So you have a third times t to the minus 1 over 3 times t to the minus 2 over 3, and you're just left with 1 over t times g prime. Okay, and then you go on and you work out your next derivative in much the same way. Once again, your t to the minus 1 over 3 is coming in here, and you have two derivatives, and then this thing is there. Okay, you now go ahead and you substitute this assumption back into your KdV equation, and you're left with this thing. Okay, so once again, ordinary differential equation, third order, but there's a catch. Okay, this is one that there's no way of solving in terms of normal solutions, but there's a lot can be said about it. So in your second year, you had various techniques for solving PDEs. Oh wait, there's one thing, let's see. Okay, you had various ways of solving PDEs, right? You could do that P substitution, you could try and factor them, you could do all sorts of things. And they're typically, I think there are 5 ways of doing it, and that's all. And all second order differential equations can be either reduced to those ways, or if you can integrate them at all, they can to be introduced. There are, I think, something like 3 Painter-V equations, 3 equations that look as if they should be solvable, but actually are not. But a lot of their properties are known, and these equations actually appear in very many places. Okay, and the guy who studied it was Painter-V. You can still get at getting estimates of the solutions using like the generalized Frobenius method. Anyway, so this is basically just the class of ODEs beyond which you would have exposed. Usually people try and avoid those because they're hard and you can't write like elementary functions down. But the majority of other second order equations you actually can. Okay, so it's possible to take this beast and to rewrite it this way. So I just want to give you an example of a Painlevé equation that you can get a feel for it. Okay, it's got a cubic term, so it's nonlinear. It's got this term, and there's not, usually when you did that series expansion, remember you wanted the derivative power and the power of y in front of it to be about the same, and this one isn't. So you can already see that you could be in a little bit of trouble. But anyway, people have solved it. And the property it has is it has movable singularities. Okay, so there's actually, and there's ways of describing this. And in fact, who was here? There was a student here that went to Stellenbosch that worked with Andre Weideman. I don't know if you ever met him. Marco. You never met him. Anyway, he is actually quite good at finding numerical methods for solving these Painlevé equations. Once again, you can see them on the complex plane, and there are a lot of people interested in it. And his PhD thesis was looking at it with Andre Weideman, and he did some really good stuff. They appear in the field equations as well, some places. So that's the reason why I know about it. And they also appear in a lot of systems that actually have this integral properties. Okay, so just here's the detail, not solvable in normal elementary functions, but their properties are known and they're found often. Okay, so that's all you need to know about that. There is a similarity solution. You can solve it. You can get a lot of control over the solution even though you can't write it down explicitly. Right, so now let us go to the general way of solving the equations. And I'm going to give you just the idea, and then I'm going to show you what type of solutions are possible, because that's fascinating, and that's sort of the inkling, it's sort of on the forefront of what people are doing and where you can actually start applying these methods to different problems. It's sort of toekomstmuziek if ever you come across it. I at least want you to know that this theory exists. And I find the way they solve it very clever. Okay, so general method for solving the KdV equation. Okay, so, and once again, we're going to solve it t greater than 0 on an infinite domain. Okay, and we're given just the initial condition on the infinite domain because we have one time derivative. So the way it goes is I'm first going to sketch the method and then apply it. Okay, and work out some of the consequences. So what we do is let's consider the Sturm-Liouville problem that we looked at in lectures 22, 21, and 23. And it's usually for a bounded function, psi of x, with some parameter lambda. Okay, and we're going to solve it on the whole real line. The problems we looked at over here were like between a and b, but you can actually transform the whole real line to a and b with a clever transformation. In fact, we'll do it explicitly. Okay, so this is what it is. Okay, and this is maybe even a more simplified version because we haven't got the p and the q in. We've just got a potential u of x over there. And typically this you get in quantum mechanics. This is where the ideas, in some way, the way of visualizing comes from. So what we now want to do is consider the Sturm-Liouville problem, except that you have a potential here, u of x, that you don't know. And you want to solve it on an infinite domain, and you have a real potential u. And what I'm now going to do is I'm going to define certain things. I'm going to define something I call the scattering data. And the scattering data is what the solution behaves like at infinity. Okay, so you basically have, so it's basically the form of the solution asymptotically. As x goes to infinity, we know it can either go to 0 or it can be a wave that travels out. So for example, what you have, and you can think of it typically as a quantum mechanics scattering problem. That's effectively what you do when my sister does X-ray diffraction. She sends, you have a wave that you send in, okay? You have this potential thing over here. The wave is going to either pass over, part of it's going to be transmitted, part of it's going to bounce off the thing and be reflected. And what these amplitudes are far away from this potential is what you call the scattering data. Okay? So now there's certain, it's easy, or it's not easy, it's always possible for a given U to work out what these things are. Okay? And basically, there's a theorem that actually tells you that the scattering data, in other words, the functions B and A, which depend basically on the wave number you've sent in, is uniquely determined by the potential. In other words, put in a different crystal, you're going to get a different diffraction pattern. Okay? And you know that two different crystals will not give you the same diffraction pattern. So that's all that it says. Okay? So that's the scattering data. It's also known as the scattering problem. How do you determine the scattering data from the wave that comes in? Okay, and there's a field of it. I don't know if it started before quantum mechanics. It must have. Whenever you have like a mountain range or in your planetary system, your waves go over it. That's going to cause your airflow to change, and it's also a scattering problem. How far away from the mountain will your airflow look? It'll determine whether the thing rains or not, and it determines your cloud formation, like an ocean as well. If you're defining, if you just like I said with the harbors, if you have an ocean current coming past, that's a wave number with a certain frequency, and then you put something in its way, you want to know how that wave number is going to change, and how much of the waves are going to pick a certain amplitude. And so it was a problem that existed even before quantum mechanics. Also, the second part is, and this is a much, much harder problem that you can do. Given the scattering data, you can actually determine, or given all the scattering data, you can determine the potential uniquely. That is at all not obvious. It took people a long time to know how to do that. It's also the reason why the black box that actually works out the crystal structure sometimes fails, because it's a very hard problem to solve. Okay, but you can once again show that it can be solved uniquely, even though you can't always in practice do it easily or numerically. Okay, so if you have the scatter data, you can reconstruct what this potential is. Okay, it's a hard problem, and it's known as the inverse scattering problem. So you have the two things. You have, give me a potential, I can work out what the waves will look like far away. Give me the waves far away, and I'll tell you what the potential is. It's basically like, give me the crystal, I can work out what the diffraction pattern is. Give me the diffraction pattern, I can reconstruct, in principle, what the crystal is. Okay, so, and often we depict the scattering data as in the following way. It's basically what the solution, it's just little waves, but the amplitude of the waves varies. So for linear problems, in other words, where the potential is not there, okay, what you have, it's basically the Fourier method, right? So for the linear problem, what you typically have, just like in the last class where I worked out what the dispersion was, and I proved that you could use the dispersion relations to actually evolve what the waves look like, and then Fourier transform it back. This is exactly what I'm suggesting you do. So here you basically start with your initial condition. You want to solve the PDE, and what you did is you took your initial condition, you did the Fourier transform to get its Fourier coefficients. You time evolved those Fourier coefficients because you knew what the dispersion relationship was. Because you knew, for example, omega k was, for example, k minus k to the 3, or 1 minus k to the 3. So then you could change that, and then you took the inverse Fourier transform, and you found the solution. Okay, and so that's for linear problems. And the amazing thing is, for the KDEV equation, you do almost exactly the same thing, but the mechanics of it is harder. So what you basically do is you start with your initial condition, with your initial potential, okay, you work out the scattering data, okay, and that gives you basically what these B's and the A's are, okay, and then you work out the time evolution from your equation of how the scattering data evolves. And how this thing simplifies the problem is very, very often to work out the time evolution at infinity, because you're only working at infinity. This term isn't there. And so the time evolution, because it's quadratic, so it's going to fall away faster than the other. So the time evolution is basically fixed by the linear part, which you can easily work out just like the Fourier stuff. And then what you're going to do is then you have your new scattering data, you solve the inverse problem, which is really hard, but you can get the answer. So in principle, you can actually solve the problem. And this is how you can solve the KDV problem in general. Now, to see how the actual solitons start forming and what solutions are possible. Sorry, do you have questions here? Okay. Okay, so let's first take an example, and for that Fourier, for the scattering problem. So let's say our potential is minus u0 sec squared of x. Okay, and so let's find the scattering data of that. So it's basically you have a potential that does that, and you want to find out what the scattering data is actually. And so we have our Sturm-Liouville problem. And what we do is we first want to cast it into a finite domain, because we're used to working with finite domain Sturm-Liouville problems. And the way to transform this thing into a finite domain is usually a tanh, because that will take your, or a tan. Oh, no? Let's see. It's tanh of h, yeah. That will take your infinite domain to a finite gap. And so we basically, let's have a new variable t, which is equals to tanh of x, and t goes from minus 1 to 1 as x goes from minus infinity to infinity. So your tanh is basically doing that, and it has the asymptotes at minus 1 and 1. So we've transformed the domain, and now we're simply going to transform the equations. So d dx is simply sec squared of x ddt, which is equals to 1 minus t squared ddt. And so if you then replace ddx over there, you simply have 1 minus t squared ddt, big bracket, 1 minus t squared ddt of psi is equals to lambda times u0 times 1 minus t squared of times psi. Okay, and I've multiplied by the 1 minus t squared over here, divided by it to get it in the formal Sturm-Liouville form, and it cancelled the 1 minus t squared over there, and you're left with this. Okay, so that's our Sturm-Liouville form. So we now have exactly what we've been working with in the past. And the nice thing is, there's actually, this is actually a known equation. You can solve it. You could once again solve it. Okay, so this thing is called the associated Legendre equation. People have looked at it. It appears actually whenever you work in 3 dimensions and do the wave equation, it also appears a lot. Whenever you do quantum mechanics, you also come across this equation. Classical Sturm-Liouville problem. And the way you do it is, let's now look at some of the solutions. So here, just to give you an idea, this is actually a sketch of this scattering problem over here. So you have the sec squared, so this is the potential, where you have u of x equals to minus u0, and then you have this idea where you have the wave coming in, the incident wave, the wave that is reflected, and the wave that is transmitted. Just out of curiosity, when you we've had methods of solving the equations, right? If we have an infinite domain, typically we take the Fourier transform, and we have this wave number is a continuous thing. If we have a box, right, then we use the sine and the cosine, and the waves are chosen that they fit in exactly. And so there's a discrete spectrum for the box and an infinite spectrum if you have an infinite domain. What do you expect to happen here? Okay, so if, oh goodness, sorry, let's get him back. So suppose, oh, why is it doing that? I'm losing my pointer. Oh, okay, it's back. So suppose, sorry, I've lost my, it's being very responsive, too responsive. Okay, so I'm not going to touch the screen. But suppose, how shall I put it? Suppose you have a valley and suppose you have wind blowing over it, right? What can happen? If your wind has a high frequency, right, it'll just blow over the top, it'll might change a little bit, some of it will bounce, feel the valley and maybe bounce back, but most of it will just continue on. So for K values that are large, there will be very little impact. Okay, and then you can change it, and then you'll have certain values that might be the size of that valley, and there you can expect trouble. Okay, and then you'll have other cases where you can actually have like this little eddy that gets stuck in the valley. So you're going to have two distinct types of solutions. You're going to have the one case where it effectively you don't see the valley and it's just waves, like it's basically your Fourier method where you have this continuous spectrum. And then you're going to have other cases where you actually have these discrete lines coming in. So you're actually going to have both possibilities. And the general thing, if you have a potential like that doesn't have a distinct finite walls, you're going to always get both. You're going to have this continuous spectrum and you're going to have bound state solutions that have discrete things. And you can actually see it come out of the mathematics. And I'll try and show it to you, but I just most importantly, I want you to have the idea of what happens. You see it as well when we work in everyday electromagnetism, right? Mostly if you shine light at an object, the light goes past, some of it gets reflected, some of it moves back. But there are very unique frequencies that if you hit the potential, because that object that you're shining is made up of atoms, and if you hit the frequency of the atom's potential of the electron shells, then that light will disappear. Okay, and those are your bound states. There are discrete lines there where your light actually gets absorbed by the atom, and that corresponds to basically the thing getting stuck in the potential. Okay, it's generic. It happens for any solution, Schrödinger's equation, that you solve with these methods, and it's built into your differential equations. Linear, nonlinear is always there. Okay, so you're always going to have a continuous spectrum where the waves just pass over, and then when your waves start becoming comparable to your container, you're going to have this discrete spectrum coming in. Okay, and so the scattering data is actually both of them. Okay, so firstly, let's look at a special case where u of 0 is equals to, so there's a distinct amplitude is equals to n times n minus 1. Okay, and then, and n is an element of z, and then you can actually say, now let's look if lambda, which is the streamable parameter, if it's negative, okay? And in this case, it's going to basically be the bound state solutions. So if lambda is negative, you can think of it having a low energy, so it's going to be very, very sensitive to what the box looks like. That's going to be your bound state solutions, and we're going to basically find them, and to find them, it's actually easier to work with this equation rather than the picture that we have on the right. Okay, and the way we do it is you can say you then solve the Sturm-Liouville problem, and you basically can find the solutions, and I won't ask you to do that, but I might ask you to verify that the solution exists like I did in the test. Okay, so what you find is that you only get solutions where kappa, or this is lambda, are integer values. Okay, and it once again has this property that it has its zeros, and the solutions are proportional to these functions, which is basically a square root of 1 minus t squared times a polynomial. Where the polynomial you can actually find, you can do the same thing as you can solve it with that infinite series, and then you can work out the coefficients. You once again get recursion relationships. And you'll find that the recursion relationships' coefficients you can summarize as simply writing this thing as the nth derivative of t squared minus 1 to the n. So you can see over here, this Pn is always a polynomial. Okay, and the most general solution then is simply the square root, because there's the n over 2 over there, times a polynomial times another polynomial, and you can show that that always solves this above equation. So you have a whole bunch, sort of a whole hierarchy of solutions with more and more zeros, and once again n actually gives you the zeros that are there. Okay, so it's nice. This is actually very nice to play with it, because these Legendre polynomials actually, when you solve spherical problems, you have these orbital things of the atom. These are Legendre polynomials in another variable system. Okay, all the structure of the three-dimensional orbital space of a hydrogen atom comes from these functions. Okay, so and they're very nice to play with. So let's just do an example. So P2 is simply, if n is equal to 2, is simply equals to, you take the second derivative of t squared minus 1 squared. Okay, and then you basically get this expression. So it's a polynomial, and then the associated Legendre polynomial, so this P2n, n then goes from 1 to 2, okay, and so you have the P21 is simply minus 3 times t times the square root of 1 minus t squared, and the P22 is 3 times 1 minus t squared. So what you're basically having inside here, you're going to have hump functions that decay to 0 very quickly, but are non-zero inside the potential. And those humps are going to be described by these functions once you have taken the arctangent of t. Okay, so you're going to have in x, you can get back to what the humps look like if you simply replace t. You can simply replace t with a tangent of x, and then you'll have exactly the humps that you want. Okay, and you can once again normalize them with a weighted norm that they have 1, and I think in fact these are normalized. And so lambda 1, when lambda 1 is equals to minus 1, you can go back and you can actually write down what the function looks like, and it's just simply this thing where I've basically taken my my Legendre polynomials and reversed them. And lambda 2 is basically minus 2 squared, so that's 4. Okay, and then you have psi 2, which is equals to 3 over 2 sec squared. Okay, so those are the bound states, which corresponds to your box where you have the things fitting in. Excuse me, as the energy goes up, you have a continuous spectrum going in. Okay, and I'm not actually going to, but you can actually, going through, you can imagine you have sent a type of radiation in, it gets here, it's just a traveling wave until it gets here, it feels the potential, some of it's going to go on, some of it's going to bounce back, and you can actually work out the entire solution to this problem that does it. People have done it, and it looks like that. Okay. Also, this is basically the general solution to this Legendre associate polynomial. It's also used a lot in quantum mechanics and in scattering. Once again, but in 3 dimensions, because you're scattering off of these density clouds of your atoms. This is the full function. We're only interested in the function at infinity. So this you don't need, but basically a hypergeometric function is a way of parameterizing the general solution to a Sturmovil problem. And the parameters that enter it, you have a series expansion, you have ways of working with it. And what this basically does is it gives all the parameters that enter into it that's dependent just on the potential's amplitude and k. And then asymptotically, which is actually the only thing you needed, you didn't need to solve the whole problem, you just needed to find what is asymptotically, you find that this function that I've given over here behaves like ak times e to the minus kx as x goes to minus infinity, so that's that term. It behaves like this when it goes to positive infinity. And so from this, you can actually read off what your scattering data is. And so what you do is you force these two to have an incident wave of 1. So you choose AK to actually be that mess. And then as a result, BK, which is this the second part over here, is equals to that. And that's what you call your scattering data. So I'm just telling you, you can compute it. Don't worry about how. But the thing that I want to tell you, what I want to say now, is what is interesting is there are potentials in which you can have an incident wave. Generally, you can have both. There are potentials that you can have an instant wave and a transmitted wave, okay, but there is no reflected wave. Okay, and your transmitted wave is not equals to your incident wave. And those potentials is basically when BK is equals to 0, and that's your reflectionness potentials. Okay, and that happens for a very particular u of x. In fact, the u of x for which that happens is exactly this one. Okay, so your reflectionless potentials are related to your bound states. That's the only take home that I want you to know, is that from this whole thing, is that there are, you have this idea that you have the waves going back and forth. The potential has an impact. Your reflectionless potentials, in which it basically, the wave either goes on or it's absorbed into the thing, is exactly the potentials that have solutions for the Sturmovil problem down here. Okay, so those two things are very closely connected. Okay, and what is also going to turn out is that these reflectionless potentials are actually associated with your Soliton solutions. So typically what you can do is when you get your U0, when you get your initial condition, you then work out the scattering data for the whole scattering data, and then you're going to find your reflectionist potentials, you're going to find your Soliton solutions, and then you can evolve them, and then that's your answer as you go back. Okay? So let's just see what that means in practice. Okay, so I'm now going to give you pictures of the solutions so you can get a feeling of what's possible. So, okay, so the discrete eigenfunctions belong to the class of reflectionist potentials. So there's a connection between the two. Okay, so I've been talking a lot about the scattering problem. I haven't told you how you actually get from here to the scattering problem. So I'm going to tell you that quickly, and then I'm going to give you examples of the solutions. So to get from here to a scattering problem, and this was years and years of work because they didn't know how to solve it, but they guessed they could because they saw such clear, solid solutions. And the way they did it was basically to do exactly that method. It actually helped lead to developing that method. So the first one is the KDV is Galilean invariant, which basically is another one of those things. If you do this, okay, in other words, you change your x variable to x plus 6 gamma t, and you add lambda, then you once again have a solution. Okay, this is not in the class of solutions that we did right at the beginning. Remember, we just rescaled x and we rescaled t. This is something else you can always do a linear combination of the variables and exchange that. It's a more general thing than what we did. Okay, anyway, it is Galilean invariant. Okay, that leaves the equation unchanged for all lambda. And so what we're going to do now to change it into a scattering problem is we're going to say, let there be a new function v that is the solution of this first order PDE. Basically, v of x plus v squared is equals to u. And this, the reason why they guess this is experience, I guess. They call this, it's a certain type of transformation that you often try. That's all I'm going to say. To make your things easier. And I'm missing an S. It's also called a Riccati equation for V. It happens a lot when you actually have waves. Okay, and so what we're basically going to do is we're first going to let u equals to this, but this is a nonlinear equation. But it's not if you set v equals to psi of x over psi. Okay, so you first do this transformation, put it in there, then you put v equals to psi of x over psi, and if you do that, you get that v squared plus v of x is psi x over psi. Okay, and that you can do simply by differentiating this one and comparing it over there. Okay, and that's equals to u. And so now what we have, we can use the Galilean invariant to let u goes to u plus lambda or u minus lambda. And so what you then get is a Sturm-Liouville problem. Okay, so I'm just telling you the steps of what it takes to actually cast the KDV equation into the Sturm-Liouville problem. Okay, and so what you do now is you start with initial condition with u, you work out your scattering data for here, then you get them. Then you can go back over here and say far away, this part is not important because it's small and it's quadratic. Therefore, the scattering data asymptotically is just the same as the dispersion relationship. You evolve that, push it back, and then you actually get your answer. Okay, and then this lambda changes in time. Okay, so I'll just quickly, I don't even know if it's worthwhile. Okay, so t equals to 0, you get that. You solve the scattering problem, you get AK and BK. In fact, if we choose f of x to be that Cinch potential, we've already got it. You get your possible bound states or reflectionless potentials, all those n things. And if the time evolution can be determined, then you know the scatter data for all later time and you go back. Okay, so you get AK of t and BK of t, and these the reflectionist potentials and their amplitudes, and then you construct U. Algorithm, easy in theory, quite complicated to do in practice, but you can actually do it. Okay, so for the KDV equation, it's just the things we worked out. The wave numbers are the reflection potentials. How they change in time is just this k to the 3 that you expect from the dispersion relationship. The AK is exactly the one we derived, and it remains unchanged. The BK is 1 again. You can see this k to the 3 coming with a time evolution. Okay, so then you have to go back, and I'm not going to do it actually. This is, if you want to ever look it up, about the inverse scattering problem is the Marchenko. It's also the thing that they'll be solving inside the diffractum problem. Really nasty, really hard. It took them a long, long time to do it. So what it basically is, if you can solve this integral equation, and they show you can, where f of x is made up of the scattering data, then you have the answer. Don't worry about it. It's chapters in a book. Okay. Then you basically, from the solution of k, you can get what the KdV equation is. And the great thing is, you can actually get the exact solution. So you can solve that, you can do it. If you really wanted to do it yourself, you could. I'm never going to ask you to, but let's have a look at the solutions, because that's where all the fun happens. So the first one is the solitary wave. So if the initial profile is u of x of 0 times 2 times sinh squared of x. Okay. Then you work out the scattering data for that. You get that it's the first Legendre polynomial, and the C1, which is basically the time evolution, is this. Your BK, your transmitted wave, is 0. Remember, it's a reflectionist potential. And your F that you work out is basically that. So it's your traveling wave. And you know it's a traveling wave because it's the one that we derived earlier with speed, basically. What's it? This speed 1 over square root of speed square root 2. Okay, and then you can find your k, and you get that your solution is this. Okay, so there we go. So that's our sec. So that's the first solitary wave. The next one is if you were to take your potential to be 6. So look, the previous one, the first initial condition was 2. The next initial condition is 6. So the potential is getting deeper. The moment the potential gets deeper, and this is sort of starts giving you the properties of the solution, you have this thing. Okay. You once again, it's a reflectionist potential because that's what I chose it, except that now that k, you have 2 possible solutions associated with it. You have the k equals to 1 and the k equals to 2. And remember, you had those n things coming up. So you actually have the C of t equals to the one solution, and you have the C of t equals to the second solution. This corresponds to those 2 separate eigenvalues. And you work out your f, and you can work out your solution that looks like this. Exact solution to the KdV equation. But it gives you an idea of how quickly it gets complicated. In practice, however, it's a fascinating solution. What basically happens is, okay, so now what I've done is I've gone, okay, so wait. Okay, so this is what you start with, right? So you have this potential. This solution at times t equals to 0 just looks like your initial condition. Okay, so because that is the potential, or minus, right? So I'm plotting minus the potential over here. So that's simply the 6 times sinh squared of x. Okay, and then as time goes on, the exact solution you have, the previous one was just a traveling wave. But you must note that this shape, if you go back to the shape of the traveling waves, this has got the wrong shape. Okay, the traveling waves had 6, then it had the square root of c times x, it had c over 2, I think, times the square root of c times x minus the speed. Okay, so this shape is actually not the shape of a traveling wave, even though it's sec. Okay, what it is it's just an initial condition. You work out its scattering data, you find it's actually made up of 2 different bound states, which are these two. And then you can write down the full solution, and what it behaves like is it simply breaks up into two things that eventually effectively become traveling waves. So asymptotically, if you look at the solution, you'll find that it's broken up into two things that have exactly the independent traveling wave solution. Okay, so the traveling wave solution over there, be careful, you can't just add them together because it's a nonlinear equation. You won't find a solution. But asymptotically, it's a very good approximation of a solution. And so another feature of this solution is, let's go back, so I'm just taking back it in time. Normally, and it's a feature of many nonlinear systems, normally when you have two types of waves, you have superposition. So if you have in your wave equation, we did that problem initially, we started with two initial waves like this, you could let them go towards each other, they superimposed, and then they went on, they both traveled with their fixed speed. You have a similar idea of nonlinear superposition in these systems. Okay, so you again have the idea that the two waves are going to come towards each other. When they get to each other, they're going to add together, and then they're going to continue. But what we see here is a different thing, right? So normally, if you had two waves coming in, if it was a linear system, what happens is you start over here, so the tall wave behind, and this is as time goes up, and the slower wave in front, like over here. The tall wave, because it's traveling faster, is, say, going to catch the slower one. If it was a linear system, they would just cross and continue riding on like that. What happens in the nonlinear system, and what the solution gives exactly, is that here, when they get close to each other, they start interacting in a nonlinear way. They slow down. Okay? And so once they're done, okay, so here it's highly nonlinear because they're messing each other up badly. It's also not quite as high as what you expected the solution to be. And then they actually go on, and then far away, they again behaving like independent waves over here, but it hasn't been a collision that you'd have said elastic, as being elastic, or excuse me, in any way normal. Compared to normal waves. So it's a nonlinear wave phenomena. And it's kind of nice to see it with the exact answer, right? So this is the exact answer that you get. Okay. So there are, and it starts making you question about, like, there's some old articles of why electrons stay bounded, why there are these interactions that we see. And it starts becoming, it's not something you can get just, because it took people a long time to go from the wave model to the particle model and back. And there's always been this tension. And this starts meshing them together in quite a nice way and gives you ways of thinking about them. Okay, so that's a two-soliton solution. You have this non-linear interaction phenomena. Asymptotically, they look like independent traveling waves, but independent traveling waves you can't add together. But you can actually find the exact answer here over here. Okay. Let's go on. Okay, so that's just summary slide for the picture. Okay, so here is just an example. So our first potential was -4. This potential was -12. Okay, so it's an even higher amplitude. And that potential I've also chosen so that it's n times n minus 1. So that one then goes ahead and it breaks into 3 solitons, each with their speed, and those will just carry on for the fastest one will run, the highest one will run away from the others. They also have nonlinear interactions. They can also. So the larger your potential goes, if you're sticking to this n in between, this n times n minus 1 potential, you break into solitons. So now, what happens if you choose something between these potentials that make solitons? So let's just go back. Oops, I'm cheating. Oh, giving it away. Right, so over here you had 6, which broke into exactly 2. Here you have 12, which breaks into 3. Here you have 4. Okay, so 6 breaks into 2, 2 broke into 1, and here you have 4. So it lies between 2 and 1. What happens? So the first thing, if you work out your scattering data, you're not at reflectionist potential, so you're going to have some B running backwards. So what's going to happen is it's going to break into the nearest soliton below it, and the remainder is going to be lost. It's going to disperse. Okay. Here. Okay, wait. Here it breaks into the 2 soliton waves, and you're going to have this wave going the other way. So what actually did, it added, right? It borrowed from the dispersive. The dispersive wave goes away, and it gave something to these 2 to fill them up so that they look like the 12 one. And then it went. Okay, so you have this idea that you have initial conditions. Intrinsically in the initial condition, there's your bound state scattering data, the waves that go on. The bound states are going to remain and be solitons. The others are just going to disperse and disappear. And so eventually it always tends to break. After you've waited for long enough, it's always going to be just your solitons and the other wave is going to be gone. Okay. And now the final thing is, suppose you flip the potential over like that. And so this is once again minus the potential. There, what you're going to do is you only get a dispersive wave if you work it out exactly, and which is exactly what Thingy also saw, and it's just going to disappear. This amplitude's going to fall in time, get smaller and smaller, it's going to wiggle faster, and eventually it's just going to gone. And so you have all the phenomena stuck together, and you have this new idea that you have waves that interact non-linearly. And that's the end of my story. Fascinating set of study. Not much, nobody has gone beyond, nobody's done this for Einstein's field equations. I feel quite strongly that there should be an answer. Everybody's basically, the whole field is doing numerics because it's too expensive to try and hunt for it. And yeah, that's it. Questions?
What should I be able to do in XM?
I've got some example problems
Okay.
that I'll give to you, that you can get an idea of what I'll ask. Basically, well, definitely not the scattering problem. Basically, you must be able to derive the traveling wave solution. You must be able to find the self-similar solution, which you already do. You must be able to do the Fourier transform waves of the dispersion, like all the easy problems that I did to illustrate it. This last is mainly just to give you a feel of what's possible and to give you a feel of how, in some sense, this idea that you have a continuous spectrum if you have an infinite domain and you have a bound spectrum if you have a box, and that when you have something that looks like the combination of the two, you have the transition between the two. That's something it's basically to give you that idea. So in future, when you get a test and you have an infinite domain, don't give me a box spectrum. But yeah, so it's like the easy calculations that I did. And then if there's something else, no, I think I'll give you some examples so you can see what I've asked in the past, and most probably will ask very similar things again. And maybe to play with the Legendre polynomials, but then the question will be like the one in the exam where I sort of step you through it, and like the properties